Given the graph of f, evaluate the following using approximations when necessary. So remember that the derivative just stands for what is the rate of change at that specific x value on the function. So for example, I'm going to skip straight up to letter B. If I was trying to find the derivative of the function at x equals -2, I'd go to x equals -2. And luckily here, this is a linear function, so the rate of change is constant, and it's what the slope is of that line. So that rate of change is up 2 over 1, so it's 2. Now there's a difference between finding the derivative of a point, which again is the rate of change of the function at that value, and finding the actual value of that x value within the function. So the f of -2 means when you have -2 in, what is the output that the function gives us? And the output the function gives us is 1. If I looked at letter C, what is the derivative of the graph when x is 3? So when x is 3, I'm right here. Again, we're on a linear function, so the rate of change is constant, and it's what the slope is of the line. So that's over 2 up 1, so it's 2. The derivative of the derivative of the function when x is 6. Also on a linear function, so finding the slope of that line, we go down 4 over 1, so that's going to be -4. The derivative of f of -5, so that's going to put us over here. So now we're not on a linear function. So in order to find that derivative, we're going to have to find the slope of the tangent. So we're just going to kind of estimate that. So I've just kind of drawn a tangent line that touches the curve right at that x value of -5, and we can estimate what the slope of that tangent line is. So it looks like we're going over 1 and down 1/2. So we'd say the slope is, or the slope of that tangent, which is the derivative at -5, is -1/2 over 1, which is just -1/2. And now if we looked at what was happening with the derivative of the function at 4. So when x equals 4, we're right here. Now, if I'm trying to find that rate of change, I'm going to run into a little bit of an issue because as I approach it from the left, that rate of change is positive. It's up 2 over 1. But when I look at it going from on the right-hand side, what that limit is as I'm approaching 4, I see that that is negative. It's that -4. That's the slope of that line. So because the limit as you're approaching 4 from the left and the limit as you're approaching 4 from the right are both not the same values, that means that limit doesn't exist, which means that the derivative does not exist. There is no constant rate of change that's happening there. Okay, let's look at another example. So for f of x equals the square root of x, find the derivative of x at 1. So let's go back and use our formulas. I'm going to stick with using the limit as h approaches 0 because we're going to end up using this a lot more in the future, and you'll see that play out pretty soon. So the limit as h approaches 0, so that formula was the limit as h approaches 0 of f of a plus h, so our a value is 1. And let's actually say what I'm doing. I'm finding the derivative when x is 1. So a plus h minus f of a all over h. Okay, so this is taking the limit as h is approaching 0. When I put 1 plus h in for x, I'm going to get the square root of 1 plus h. And then I have minus, when I substitute 1 in for x, I get the square root of 1, which is 1, all over h. So this is again where right now, if I'm looking at this, we're in that indeterminate form. We have 0 over 0 if I substitute 0 in for h. So when we do that, we've got to go back to those problem-solving strategies. One of the strategies said that if you had a square root and it was the difference of terms, that what we can do is we can multiply both the numerator and denominator by the conjugate. So let's do that and see if that'll help us out. So I'm going to multiply both the numerator and the denominator by that conjugate, which is going to be the square root of 1 plus h plus 1. And again, I've got to keep this equation balanced. So I do the same thing to the denominator. So when I do that, let's kind of distribute this through. So I'm going to get the square root of 1 plus h times the square root of 1 plus h is just 1 plus h. It undoes that square root. And then I've got plus the square root of 1 plus h, and then minus the square root of 1 plus h, and then minus 1, all over, and I'm going to keep this factored, h times the square root of 1 plus h plus 1. So when I do that, we get the limit as h approaches 0. So we have those 1's will cancel out, these cancel out. So I'm just left with h in that numerator over h times the square root of 1 plus h plus 1. So now again, those h's are going to cancel, and I'm left with the limit as h approaches 0 of 1 over the square root of 1 plus h plus 1. Now at this point, if I substitute 0 in for h, I can actually evaluate this function. So it's going to be 1 over the square root of 1 plus 0 plus 1, which gives us 1 over 2. Let's look at another example. For f of x equals 2 over t, find the derivative at t equals 6. Okay, so let's go through and we're going to stick with that second formula, the limit as h approaches 0. So I'm finding, again, I need to start with saying this, I'm finding the derivative of the function when f is 6. I'm going to use that notation. Okay, so that is going to give me, again, it's always f at a plus h minus f of a all over h. Okay, so that's going to give me the limit as h approaches 0 of 2 over 6 plus h minus f of 6. So when I substitute 6 in for t, I get 2 over 6, which is 1/3, all over h. So right now, if I substitute 0 in for h, I'm going to get 1/3 minus 1/3 in the numerator, which is 0, and 0 in the denominator, so I'm in that indeterminate form. So we're going to go into our problem-solving strategy that we learned. So in that problem-solving strategy, it talked about if you have a complex fraction, which we have here, a fraction within a fraction, that we simplify it. And the method that I use is I'm going to multiply both the numerator and the denominator by that LCD. So the least common denominator of these two fractions is going to be 3 times 6 plus h. Okay, so when I do that, and I'm going to probably write one extra step than you probably would do, but I'm just doing this to make sure that you see that we are distributing this to every single term. I'm going to put this in parentheses, and then minus 1/3 times 3 times 6 plus h, and then that's all over h times 3 times 6 plus h. Okay, so when I go to simplify this now, these 6 plus h values cancel, and I'm left with 2 times 3, which is 6. Over here, I'm left with the 3's cancel, and I'm left with minus 1 times 6 plus h. So I have to remember that this negative applies to the entire quantity 6 plus h. And then again, that's all over 3h times 6 plus h. I'm just going to combine these two. Okay, so now when I go to simplify this out, let's distribute that negative sign through. So I'm going to be left with 6 minus h all over 3h times 6 plus h. Go over here, the limit as h approaches 0 of negative h over 3h times 6 plus h. So now these are going to cancel, and I'm left with the limit as h approaches 0 of negative 1 over 3 times 6 plus h. And now I can actually substitute 0 in for h. So I get negative 1 over 3 times 6 plus 0, which is going to give me negative 1 over 18.